In this video we will implement the counterfactual regret algorithm. The way it is going to go is that I will first explain each piece by sketching it out in Excalidraw and then writing down what I've explained in code. Let's start from first principles. Imagine a game tree, something like you see on the screen here. And then now suppose that each of these terminal nodes has a reward at the end. Assuming that the player starts at the leftmost action, what would be his reward at the end? Well, the question doesn't really make sense when posed like that. You'd say that it depends on the path that he takes. So, for example, suppose that he took a path through the upper route, like this. Then, at the terminal node that he reached, his reward would be 1. But if he took a different path, maybe he'd get a reward of 2. So, either 1 or 2 in this case. Games like poker, you don't just play once and never again in your life. So assume that the player has a lot of trials at his disposal. If he takes the first path 50% of the time and the other 50%, then those two paths will average out to a reward of 1.5. We can write down the probabilities on the game tree itself as follows. You can just visualize it as the player going forward through the game tree and the values, or the rewards I mean, flowing backwards towards the beginning. The arrays of probabilities at each action node, like the ones you see on the tree there, are called policies. At each node, to get the actual rewards, you just multiply the incoming rewards by their policy probabilities and pass them backwards. Let me show you what I mean in code. Now we are finally getting to the part where we are implementing an actual learning algorithm. This kind of type should be familiar from the previous video, except it is more abstract. What the actions are should be self-explanatory. We need the algorithm to pick one of them before passing them into the continuation for the game to proceed. The model, on the other hand, is all the information the player has at his disposal. For example, his own card and the past moves of the game, but not his opponent's cards, which are hidden. Next, let us look at the partial implementation of the counterfactual regret algorithm. We'll assume that a getPolicy function is given. If you study the action member of the interface, you'll see that what is happening is exactly what I've described in that sketch. We get a policy, push all the actions into the continuation to get the rewards, and multiply those by the action probabilities. Then we sum them up. The reward flows backwards through the graph. So far, what we have is only a system for going through the game tree to get the rewards. But in order to get something useful out of that, we need to have a way of improving the policy. In the graph you see on the screen there, it would be better if the player picked actions which lead to a higher reward. Let's imagine how we could implement that. We can introduce a new function, let's call it update policy. And in order to update that policy, all we need to do is pass the rewards into it. Maybe we'll reify the average reward and pass it in as well, just in case it needs it. Of course, we also need to pass in the model, otherwise the update function wouldn't know which policy to update. It might seem that an algorithm of this sort should be all we need, but in fact it is missing vital information for it to work. I'll explain what is meant by that. Going back to Ledak, imagine a really heated game where both players, one of which is you, are raising to the limit. In the last round you raise, then your opponent re-raises, and you have an option of either folding or calling. You'll have to make an action. After you make it, you'll get a reward and update your policy. You don't know what hand your opponent has, and if you were just enumerating naively like this algorithm does, you wouldn't be able to tell the difference in how frequently you arrive in that particular state relative to what your opponent is holding. Consider it like this. Maybe your opponent plays really tightly on the final street and would never re-raise you unless he had a pair. But if you are just enumerating the possibilities, the program would have you do the policy update with equal measure for all the possible hands that your opponent has in that state. But if he can only ever have a pair, then you'd want to discount those other hands by the probability of them occurring. This isn't hard to implement, let's do that right now. First, we need to introduce a path probability type. This will just be a pair of floats, representing the path probability of both yourself and your opponent. The algorithm needs this information if it is to have a chance of working correctly. We'll make a little helper to multiply the path probabilities with the policy ones, and then use that before passing the right arguments into the continuation. The update policy function also needs those path probabilities in order to work correctly. Looking good. With this, we've sketched out all the essential features of the learning algorithm we are working on. Next, we need to implement the two given policy functions. For the getPolicy function, I'll introduce a dictionary. Given a model, the function should just get the policy array if it is there, but if it is not, then it should make a new one, store it in the dictionary, and return it. Here is the implementation. Getting the policy was easy, but actually updating it will be more involved. First of all, how is the policy represented under the hood? As you can see on the screen here, like an array of non-negative floats representing the accumulated rewards. The negative rewards are just clamped to 0 should they occur in the array. And to get the policy probabilities from this, you just normalize the array so it sums up to 1. Looking at this, you might be wondering how could a fold possibly have positive reward? Imagine if you were in a poker game and facing a big raise with a weak hand, and your opponent has a strong one. In that case, folding would give you a weak negative reward, calling would give you a moderate loss, and re-raising would give you a large loss. Suppose you subtract the average reward for all the actions from that. Then the fold would actually turn out to have a positive reward, and these centered rewards are what you would be using to update the policy. Now that I've explained this, I realized an error in the code that I've written earlier. Let me go backward so I can correct it. For the rewards you are passing into the update function, you don't actually want to multiply them by the policy probability beforehand. Let me fix it quickly. When calculating the average reward, you definitely do want to multiply it by the policy probabilities. By now we have all the essential features of our update algorithm in mind. We know that we need to use the raw rewards to update the policy, we know that we need to center them before that, and we know that in order to get the policy probabilities we need to normalize the array before returning it. Let's implement that in code. We'll start off by including the normalization. It should be done in the getPolicy function. I forgot to do it last time. The way it works is simple. You sum up the non-negative array of the centered rewards, which are called regrets, and then divide it by that value to get the policy probabilities. If it happens to be 0 like it would for a freshly initialized array, just set it to an uniform distribution. Next comes the updatePolicy function. First, let's do some refactoring so we can use the getPolicy function inside the update one. Now we can get the actual policy that is unnormalized. It would be right to call these the accumulated regrets. After that, we'll get the current regrets by subtracting the average reward from the rewards. Then we just add them together. But if we did that, we would be forgetting about one thing, the path probabilities. Let's include that. If we wanted to include the full path probabilities, we'd do it like in the actor-critic algorithms, which is like the following. We multiply the current regret with both our own path probability and the opponent's path probability. In Bayesian terms, this is like conditioning on both our own and the opponent's actions. But instead of doing that, we can make the algorithm more efficient by removing the unnecessary and instead take our own actions as given. To explain why that is, imagine you were skydiving out of a plane, and while you are in the air, at some point you have the choice of picking whether or not to open the parachute. Suppose you were deathly afraid of heights, so that you'd never make the choices to get into such a situation. The algorithm we talked about and implemented here, the actor-critic algorithm, it would never learn anything in that situation. And the reason is exactly that self-probability term. If it is 0, then it cancels out everything else. So we'll improve the algorithm in an easy way by getting rid of that term. At this point, the brighter among you might be thinking, is this it? Is this why the brain models the self for the sake of isolating its own actions from the world around it so it can do imaginative thinking and reasoning? And the answer is yes, yes it is. While I'm joking, I don't think this is too far from the truth. Ultimately, it is insights like these why you'd want to study machine learning. And in the case of the counterfactual regret algorithm, while it doesn't say what the brain does, it does have a lot of say about why the brain should do it. Because if it didn't create the self, it wouldn't be able to discount it from the rest of the environment. Let's get rid of the self probe and then we'll shove this new regret array into the dictionary. Then we'll be done with this particular function. That takes care of the update policy function. We are not done with the algorithm yet though. While it is true that if we run this on a static game where the opponent doesn't learn or adapt to the player, it would converge to the optimal policy, the same couldn't be said for games like poker, where both players are trying to outfox each other. Forget poker. If you tried running this on a game like rock, paper, scissors with the both players trying to adapt to each other, what would happen is that the policy would oscillate wildly. It would go from betting rock 100% of the time, to betting scissors 100% of the time, to betting paper 100% of the time as the opponent adapted to it, and it would continue going like that in an endless cycle. The solution to that is to average out the policies. One way of doing that would be to have an ensemble of policies instead of a single one and optimize those. Experimentally, the more policies you have in the ensemble, the more precise the true policy will be when you average out the ensemble at the end of the optimization process. A much better way that would only double your memory requirements compared to keeping a single policy at each node would be to keep a policy average in an array. Let's implement it, and you'll see right away what I mean. We'll start things off by extending the dictionary. Instead of a single floating point array, we'll have it hold a record of arrays. Then we'll deal with the type error in the first function by having it fetch the current policy. Then we'll implement the policy averaging. By policy averaging, I mean averaging out the policy probabilities instead of the policy regrets. And the way to go from regrets to probabilities is to just normalize them. Now what I need to do next is to fix the wonky naming of the record fields and the variables in this to something that is more descriptive. Variable naming is a balancing act. The golden rule is to just do whatever is the easiest to understand. Sometimes you just want to pipe the values without naming them, or use short variable names like x or d, and sometimes you want descriptive ones to remind you of what the variable's purpose is. Hopefully these changes make the code more readable. As we are only adding probabilities to the policy average, its normalized form will start to converge to the true policy over the course of the optimization process, even though the current policy, which is based on the accumulated regrets, will oscillate wildly. During a learning, the average policy won't play a role, but after the learning is done, we will take the unnormalized policy, normalize it to get a probability distribution, and use that as the actual policy for the computer agent we'll be playing against. I think this should cover the entirety of the counterfactual regret algorithm itself, but it still leaves the job of integrating it with the rest of the system. By the way, this is the enumerative version of the algorithm. In a future video I'll also cover the Monte Carlo version of it. In that video I'll also go a bit more into depth about variance reduction and why it is a good idea to center the rewards. For now, let's just put this into action. I've touched up the UI a bit, and now clicking on the button will run the training procedure we have implemented. The chart is set up so it shows only the latest 150 items, otherwise it would drag down the UI. Once the training is done, the bottommost window will show the average policy for every sequence in the game. As a common sense test, you'll see that it raises strong hands and folds weak ones. I know that right now I'm just running through this really quickly, sorry about that. It is more interesting to actually run it yourself and observe and think what the numbers mean. After it finished training, we can get an estimate of how good it is by taking the trained player and training it against a static copy of itself. In the Train tab, the two curves do not mean much by themselves, but what I'm showing here is a good way to estimate the agent's quality. As you can see, these are all very low values. It's a bit blurry, but here it is showing minus 0.068. In poker in general, the player that goes first is at a disadvantage. No matter what moves the trained agent takes by training against the average policy of its copy, it can't do much better than losing slightly. If I let it train for longer, it would do a bit better, but not by much. If you recall how it was in the Train tab, after I started training, at the beginning it would very rapidly improve, but after that it would fight to get very small improvements. In a real poker game, if two players of this level would have gone against each other, they'd both lose after the rake was factored in. Anyway, let's go back to the code so I can talk a bit more about the average policy update. The average policy update is difficult to understand, and in preparation for this part of the video I've given asking around a try. The algorithm that I've shown a few minutes ago where you just add the current to the average policy is easy to understand, but it is not necessarily formally correct. What's actually formally correct is to multiply the update by the current path probability. That indeed works best, but the alternative methods are actually pretty strong too. Let's do a little testing. Implementing a learning algorithm and then wasting endless amounts of time tweaking it is one of the charms of working on AI. This particular update equation that you see on the screen here is what worked the best for me. But the original one is like this. Just multiply by the self probability. Don't do any normalization in the denominator. How does that work? The results surprised me. Whether you multiply the self probability like the original algorithm demands, or you do something else, it doesn't seem to change the outcome much. In that Reddit thread I showcased briefly, they say that multiplying by the self probability is necessary, but I haven't gotten an explanation that I feel is intuitive. But just now I did come to a realization on what the average policy update is supposed to be doing. Let me first lay down the assumptions before I explain. As I said earlier, policy averaging makes sense. If you try this algorithm without averaging, that is with just the current policy on a game like rock, paper, scissors, it would just oscillate wildly and not converge. Secondly, the current policy update that is the core of the counterfactual regret algorithm makes sense. Omitting the self probability and just multiplying by the opponents, or more precisely the environment probability, can be worked out intuitively. But when we get to the average policy update, I found it absolutely mind-boggling how the opponent probability term gets left out, and the self probability term got added for some reason. Wouldn't it have made more sense if instead you multiplied by the opponent probability? Just what is going on here? We have one clue to unraveling this puzzle, namely that the algorithm works regardless whether you use the self probability or not. I haven't shown it in this video, but it also works if you multiply by the opponent's probability, so it works with pretty much anything. Suppose I rewrote it like this, maybe it would be more obvious what the average policy update is doing. How would we restructure the algorithm so the current policy update doesn't require multiplication by the opponent probability, so instead it is done implicitly? Let's also get rid of the weight decay so the program has less moving parts to think about. Now, in order to make the current policy update equivalent to what we had before, what we need to do is update it with the same frequency. Something like this. Consider this a pseudocode and imagine that we scaled down the precision to very low values. The higher the number of discrete steps, that is updates in this loop, the closer the average policy update would get to the current policy. And on the contrary, the lower the number of discrete steps, the further the average policy update would get from tracing the current policy exactly. It would essentially be sampling it at random points. Think of this green line in the middle as the current policy, and those arrows as where the average policy update plucks it from that imaginary space. Since the current policy itself has the opponent probability embedded in its values, there is no need for the average policy update to consider it separately. As I said, I found this really confusing, but it makes sense in a CFR-like algorithm that is fully discretized. If you really ramped up the sampling rate, it would become obvious that policy averaging doesn't require any other factors to compute its average. And once you concluded that, you can assume that the original CFR algorithm doesn't need it either. But it is hard to see that there directly. The original algorithm, rather than sampling from the distribution of current policies directly, instead samples its extrema. And multiplying those by the opponent probability would just add noise. And with that I'm done with explaining the CFR algorithm. I won't even try explaining why multiplying by cell probability makes sense, because I do not understand it myself, and I demonstrated empirically that it makes a little difference. And with that we are done with this very long video. Thank you for coming along all this far. If you found this video informative, please like and subscribe. It took me many hours to make it, and it would take you only a couple of seconds to make those few clicks. In the next video, we'll integrate the algorithm into the duck game itself and actually play against the trained agents, so stay tuned for that.